Hello, everyone. Thank you for joining us today on this lovely Thursday, June 10th. We are excited to have you here. We have all our team has a bunch of travel this summer, so our schedules are going to be moving around a little bit, and we will be sending out announcements as usual. Make sure that if you are on with us today that you like and subscribe. My name is Matthew. I am one of the part of the teaching team. We have Victoria, who has been helping us out with technological stuff today. And I will hand this over to you, Chris, and then we will get started with questions.
Okay, welcome everyone to another Q&A live session for the online classes and anyone else who drops in and finds out about it. I'm relocated out of the close to 110 degree heat of Tucson to Aspen, Colorado, Center for Physics here. Very nice place to spend some time doing research, and highs of low 80s and lows of 50 at night. Perfect. Floor is open for questions about astronomy.
Excellent. And for those of you who are new to our live sessions, thanks for joining us. Just post your questions in the chat and we'll be grabbing those. We try to go in order, but we also jump around a bit to get a variety of topics since we often get similar questions from week to week. So we try to mix it up and keep it interesting. The first question is from one of our live participants who asks, could you please comment on the modified gravity theories versus dark matter?
Sure. Modified Newtonian dynamics, that's the acronym MOND, is an attempt to do away with the need for dark matter entirely. So remember, the basic evidence for dark matter involves the way galaxies, stars and galaxies move, and the way disk galaxies like ours rotate. The stars are basically moving faster than can be explained by all the visible matter in all the stars of a galaxy. And the only reasonable explanation with Newtonian gravity is that there's an unseen mass that's distributed on a larger scale than the visible galaxy, 3 or 4 times larger, and actually contains 5 or 6 times more mass than the visible stars. So it's quite a dramatic inference from the motion of stars and galaxies. This is an inference that applies whether the galaxy is a spiral or an elliptical. Basically, all galaxies seem to have dark matter that outweighs the normal stuff. But it's an extreme hypothesis because as we speak, even though dark matter evidence started to appear in the 1970s, so it's almost half a century that we've had signs of galaxies dominated by dark matter, we still don't know what it is fundamentally. There are ideas, and there are experiments, physics-type experiments to find it, but we don't know what it is. So people, for a while, have entertained the possibility that if you alter the Newtonian gravity force law, which is inverse square, if you find a physical reason why it's not inverse square, you only have to modify that exponent a modest amount to not need dark matter at all. So MOND is a family of theories or ideas that do away with the need for dark matter by modifying Newtonian dynamics. It's a little controversial because the bulk of astronomers don't think that MOND is the right answer. They still think there's a dark matter particle out there for us to find, and they have various projects and experiments to try and find it. But MOND has done quite well in explaining the properties of galaxies as we see them, and of clusters of galaxies. The criticisms about MOND mostly relate to theoretical problems with the theory. You're altering Newtonian dynamics in a way that make the theory a little difficult to execute. It becomes less elegant than Newtonian gravity, for example. It's not clear that theories have to be elegant, that Newtonian gravity is the only theory. And remember, we've only tested Newtonian gravity force law within the solar system. We don't have direct tests of it on the scale of galaxies. So it's certainly possible, without an observational test, that Newtonian gravity does change its form on large scales. So at the moment, the jury is out. The bulk of the evidence still indicates a fundamental particle, a new particle, that is the dark matter, but there are enough people working on MOND and it has had its successes so that people are using it as a viable alternative.
The next question is from Jan Campos, who asks, can you simplify entanglement a little? Is it the same as Bell's action at a distance? I'm not quite sure where to start understanding this concept.
Well, the basic experimental situation is that you can create particles. You can have particles in the laboratory where their quantum states are not independent. In other words, particles operate according to quantum mechanics. They have energy states and energy distributions and quantum properties dictated by that theory. That theory describes how individual particle, like a proton or an electron, will behave and what its properties are. However, it turns out that there are properties of subatomic particles which can be coherent over a significant distance. In other words, the properties of one particle can be correlated or related to the properties of a particle that's separated from it. And that is the basis of entanglement. That's the nature of entanglement. It's quantum properties that are coherent or distributed over space and between particles. And with very clever experiments, people have shown this quantum entanglement over significant distances, certainly in the lab over tens of meters, and with a little less directness in experiments that range over up to thousands of kilometers, actually, between labs in different countries. So it's quite a profound result. Bell's theorem is tied up with this because that states how quantum information is held in a quantum system. And Bell's theorems do accommodate the coherence of quantum states and the entanglement that we can see in the lab. People are trying to find practical applications for entanglement. Quantum computing, for example, definitely uses it because it creates coherent quantum states, whereas instead of having a single bit on, off, 1, 0, you have a qubit, which is a quantum entangled digital state. And that actually lets you code more information at a higher density using individual atoms. That's probably the most important and profound practical application of entanglement.
The next question is from Christy Reed. Hello, Christy. Welcome. The next question is, I'm reading a lot about harnessing the energy of rotating black holes. What is your opinion, Chris? Too much of a dream?
Well, it's good to talk to you, Christy. It's a dream in the sense that the nearest black hole is hundreds of light years away. So in that sense, yes, it's a dream because interstellar travel is so far beyond us, and black holes are rare remnants of massive stars. So the nearest black hole is far, tens or hundreds of times further away than the nearest star, which is only, of course, 4 light years. However, if you did have proximity to a black hole, the idea of extracting its rotational energy is actually quite simple. I think Freeman Dyson had this idea almost half a century ago, the idea that you could, with suitable trajectories of projectiles, you could send them close to the event horizon, not actually to the event horizon because they would disappear, of course, but within the ergosphere of the black hole. And you could essentially transfer energy to the projectile, and it would come out with a little more energy than it went in. And the black hole would lose some rotational energy and so spin very, very slightly slower. So the mechanics or the practicality of doing that, of having a civilization, say, that extracted rotational energy from a black hole by the judicious trajectory of projectiles that they then extracted that extra energy from, that's completely plausible. The other, of course, mechanism for energy from black holes is the Hawking radiation itself, but that's an incredibly feeble amount of radiation and not likely to do anyone much good.
Our next question is from Martina, who asks, is it possible that under certain conditions mass will be negative? Could there be a negative Higgs boson or Higgs field?
The idea of negative mass is interesting because, in terms of quantum properties, obviously we have quantum properties that have an opposite. So there's charge, that's the most intuitive one, where you can have an electrical charge, positive or negative. You can have parity, which is a spin, which is in opposite senses. And obviously there's a quantum property that relates particles to antiparticles, and that's another opposite property. It's not clear what negative mass would mean in quantum theory. So while you could sort of conceptualize it theoretically, it's not clear how that would manifest. So as a practical matter, there's no evidence in lab physics for anything that would have the attributes of negative mass. And it's not even clear how that would be accommodated in gravity theory. Negative mass is not part of general relativity, so we do not have a gravity theory that could accommodate that. And so at the moment, I think it's a very esoteric and probably not real concept in physics.
Parth asks, Parth is on with us live, and they ask, can there be a complex world for all the objects which move faster than light, as their mass will be imaginary?
Well, a tachyon, or a faster than light particle, is another concept of physics it can be accommodated in a purely theoretical sense. It's an extrapolation of conventional physics, but not an unreasonable one. The question just becomes, can you observe such a thing, and do you ever see anything with the properties that would cause it to think like, to be like a tachyon? And the answer is no. We've had some significant experiments to try and look for tachyons, or imaginary sort of particles moving faster than light. And they should have actually influence in the universe we occupy. So these limits on tachyons are significant. In other words, there's no reason to believe that tachyons are part of the real world or the universe we occupy at this point.
Excellent. The next question is again from one of our live participants. Demetris asks, do astronomers study philosophy? And do you believe that scientific discoveries enhance certain philosophical currents?
It's an interesting question, and the basic answer is no. Most scientists, not just astronomers, do not have philosophy as part of their toolkit or even as part of their undergraduate studies. Most astronomers study physics and astronomy as undergraduates, and then they specialize after that. And most scientists, it's the same thing. So I would say only a small fraction of scientists have ever had a philosophy course. And that's to their detriment. It wasn't part of my undergraduate studies, but I took one because I was at a place that offered good philosophy, had a good department, and the University of Arizona has too. So I've taken sat in on a few classes since. I think it's important for scientists to know about philosophy because it's the history of ideas behind their subject. And if you're sort of ignorant of the flow of ideas, the dead ends, the false starts, the mistaken ideas, then of course you're possibly doomed to repeat those kind of mistakes. So the philosophy of astronomy, or the history of ideas and the flow of ideas, actually is very important. And especially because astronomy is the oldest science, so we're talking about ideas that go back to the ancient Greeks, of course. And some of their ideas, have not become obsolete over 2,500 years. So philosophy is important in astronomy. The history of ideas is meaningful to understand our current view of the universe, and I recommend most scientists should take a philosophy course if they can.
Good advice. The next question is from Kinda Smith, who sent an email asking, if the space between our galaxy and the galaxies farthest from us is accelerating faster and faster due to repulsive gravitational effects of dark matter, so they would mean dark energy. But then it is true that there may be some objects in the universe which will never interact with our planet or galaxy gravitationally or in any other way?
That's correct. The current view of the universe, especially the accelerating universe, is that there are a set of objects that are beyond our horizon, as we call it. Horizon in astronomy or in physics is reference to a distance and a situation where light nor any information cannot have reached us in the history of the universe, say. And in the Big Bang model, there are definitely regions that are beyond our horizon. That is, regions of space, expanding space-time that we expect to be there. And that space-time probably contains galaxies, just like the space-time we can see, where that information hasn't reached us in 13.8 billion years, and because of the accelerating expansion, will never reach us. So yes, absolutely, there are many galaxies likely, maybe as many as in our visible universe, that are beyond our horizon. And because of the accelerating expansion, they will remain that way forever.
Ilsa is on with us live. and asks, which country do you think has the most ambitious plans for space exploration?
Well, it's an interesting question because at the moment you would almost have to say China. China has been growing their space program from modest beginnings at the rate of their economy. And, until recent turn down of the pandemic and the global recession, apart from that, China's economy has been growing at 8 to 10% a year for a couple of decades. And that means their space program has been growing at that rate, which is a doubling every 4 years or so. Contrast that with NASA, whose real budget is 2 times lower than it was 20 years ago. So Chinese still do not spend the same amount that the Americans do on space, but it's approaching it. Their ambitious plans include their own space station. We've seen them recently go to Mars. We've seen them on the moon, and they plan habitations on the moon and Mars, and they almost certainly will be able to do that. So if you're really looking at the current situation, I'd say China has the most advanced plans. United States, NASA does the best it can with its budget, but it's had some very expensive, almost failures in replacing the space shuttle, starting with the Constellation program, which limped along for 5 years and was canceled, and now with the Space Launch System, which is $20 billion and counting, and there's still no timeline for a first crewed launch. The US is doing well by partnering. NASA partners now with private companies like SpaceX, and that's accelerated progress in the US space program. Outside of the US and China, there are new entries into space. The Indians obviously have done some successful things, Japanese, Brazilians, and the Russians, of course. But the Russians are really not investing in new technologies. They're sort of limping along with the Soyuz rockets, which date back to the early 1960s. So I'd say at the moment, the only 2 major powers in space are China and the United States.
The next question is from the 800 millimeter telescope project on live with us. Is there a role for amateur astronomers to contribute to actual astronomy? Any specific areas where amateurs can collect data for scientists?
Absolutely. There are amateur astronomy capabilities are quite impressive now. Amateur astronomers have meters scale telescopes. They have sensitive cooled CCDs, and they have very good automated telescopes. At that level, you can definitely participate in research. So the biggest areas where amateurs are already participating, and more participation I know is welcome in collaboration with professionals, are on exoplanet discovery, supernova monitoring and discovery, mapping of distant objects in the solar system, asteroids, for example, counting asteroids, near-Earth objects of various kinds, and in the study of certain types of variable stars, where the persistence and cadence of an amateur astronomer observing an object very frequently goes beyond what some observatories can do because they have to split their time amongst many users. So those are just examples, but actually there's a very vigorous contribution of amateur astronomers to astronomical research at this point, and it's only growing because the capabilities of amateur facilities are improving quite steadily.
The next question is from Tian, who asks, are there ideal conditions for the creation of life when 2 comets collide? And is it possible for microorganisms to live during this moment of destruction?
The question of whether comets are implicated in the incubation of life or the formation of life is an interesting one. We know that comets contain complex organic materials, amino acids, lipids, fats, and some of the basic life-forming molecules. But they don't contain anything that we would say would be a replicating molecule like RNA or DNA. So it's unlikely that comets contain life in a frozen form or fossilized form. But they absolutely contain most of the major ingredients for life, especially phosphor compounds, which are important eventually in forming ATP, which is the energy molecule of biology. When 2 comets collide, of course, energy is produced and the material gets melted and mixed, and so possibly comets colliding would accelerate the formation of more complex molecules. But overall, comets are not a good environment for forming life. They're too small. They don't have a normal liquid medium anywhere, which is the medium we think life started in. So really their role is in perhaps seeding the ingredients of life when they impact planets early in the solar system's life.
The next question is from David, who asks, could there be extraterrestrial life on dark matter that is close to Earth, but not visible due to current technological limitations?
Biology and dark matter don't really mix very well, as far as we understand dark matter or life. And that's because the dark matter, we think, is a subatomic particle, a fundamental particle, not part of the standard model of particle physics, but an extension of it. It's very massive, and it doesn't interact with light or electromagnetic radiation. And in a sense, it's the sort of aloofness of dark matter, the fact that it really only interacts by gravity, that means it probably couldn't be implicated in biology. Because biology is, of course, based on chemical reactions, and it needs to harness energy, and that energy would come from light and radiation. And dark matter doesn't care about radiation. It doesn't interact with it at all. So it's pretty clear, even if we don't know what dark matter is, that it doesn't have any direct association with life or biology.
The next question is from Prohit, who asks, how does the mechanism of using another planet's gravity to accelerate a spacecraft work, like how New Horizons used Jupiter's gravity to speed up and reduce travel time to Pluto?
Right. So the mechanism is called the gravitational slingshot, and it's a basic application of Newtonian gravity. It's quite clever, but it's not that complicated. Basically, if you send a spacecraft close to a massive object moving fast, the gravitational interaction of the much less massive object, the spacecraft, with the enormously massive object can result in the transfer of a little bit of energy to the spacecraft, the small moving object. Now, energy is conserved, that's a law of physics, and so when the energy is transferred to the spacecraft goes a little faster, sometimes a lot faster if you use the right trajectory, and that's the slingshot. And that's how we accelerate spacecraft, sometimes from the interior of the solar system, like using Venus for the slingshot, to send things out to Jupiter and Saturn. Because energy is conserved, the planet, the much more massive object, actually does lose a little rotational energy, but it's so tiny compared to its overall rotational energy, you wouldn't know it or measure it or feel it. So gravitational slingshot seems like a way of getting energy for free by using the motions and the spins of massive objects around you to orbit, to send objects more quickly into outer regions of the solar system, where of course you're working against the sun's gravity. So you need to get close to the escape velocity of the solar system to send an object, say, to Neptune or Uranus.
The next question is from Ambika Agarwal, who asks, motion is relative. Indirectly and directly, time is just a measure of distance. Is it possible that the universe may be collapsing into some kind of big crunch instead of a big bang, and it might just be the opposite?
Well, the thing we can't comment on is what happens beyond our view, beyond our horizon. So it is the case that the galaxies we see with our telescopes, right to the edge of our vision, are all moving away from us. When we look out in space, we look back in time. So we've essentially mapped most of the history of the Big Bang expansion back to within a few percent of the Big Bang itself, 13.8 billion years ago. If there were to be a larger realm in which there's contraction rather than expansion, it would have to be well beyond our horizon. And so that means it's beyond, 40 billion light years in any direction. So you couldn't conjure up that possibility, and it's hard to refute, but it's also hard to test because everything we see is a bang, a Hubble expansion, an accelerating expansion due to dark energy. We don't see any evidence of contraction in the volume we can observe with our big telescopes.
The next question is from Shelly, who asks, what do astrophysicists consider to exist outside of the expanding boundary of the universe? And is this boundary thought to be spherical?
The shape first. The boundary is spherical only in the sense that we can look out in every direction and see about the same thing in the same distance. That's a cosmological principle, that the universe is roughly the same in every direction. That doesn't imply the universe has a spherical shape at all. That's just a distance given in every direction by the distance light can travel in the age of the universe. So operationally, we see a sphere because that's the region that light can have reached us in 13.8 billion years. Beyond this sphere that's available to us by observation, we really can't comment. Because of the accelerating expansion, we believe that regions of space-time that are very much like the one we occupy do exist where we can't see them. And therefore, logically, by the Copernican principle, they would contain galaxies and stars and dark matter and planets and maybe biology, just like the region of the universe we can see, which is pretty interesting because it means the 100 billion galaxies or so in the observable universe are a small subset, potentially, of the entirety of galaxies in the entire universe, including the part that's beyond the visible universe.
The next question is from Evanth, who asks, can we manipulate gravity?
No, we don't have that ability yet. That's a technology not available to us. We can redistribute mass. We can compact objects. Obviously, in our attempts to make fusion happen on the Earth, we try to compress matter to reach a temperature of 10 million Kelvin, at which point we can create the fusion process on Earth. And that is a large amount of compression of matter, but we can only do that for a tiny fraction of a second. That's about as close as we come to altering gravity by altering matter. So the basic answer is no, our technologies are still too primitive to alter matter in any significant way. For example, some people speculate that advanced alien intelligences, rather than sending radio waves or laser pulses, which are just our technology of the moment, would know how to manipulate matter, and therefore they would be communicating with gravity waves. Gravity waves are something that we can just detect in the last 5 years, but we have no way of generating at the moment.
Pashupati asks, after the G2 muon experiment, do you think the standard model of particle physics needs revision?
This is a controversial topic because the experimental data has passed the 3 sigma level and is headed higher. Experimental physicists hold a criterion for declaring something statistically significant that is beyond what most scientists would think is enough. 3 sigma means there's only a 0.1% chance you made a mistake if the errors are normally distributed. 5 sigma means there's less than a 1 in a million chance you made a mistake. This result was already 3 sigma and it's headed higher. So people have started to become fairly confident the experimental result is correct. However, the modeling, the theoretical side, which leads to the discrepancy with standard physics, has got muddy in the last few months. There are now several theoretical papers that argue that the prediction from theory that the experimenters were matching against was wrong, and that makes this discrepancy go away. So I think both for the experimental reason that it's not 5 sigma yet, and for the theoretical reason that the predictions from models are not quite clear, we put a big asterisk by this result. So we're not ready to declare new physics yet.
Ellie asks, how do black holes change time? I can't quite grasp the thought of time relativity and how it works.
Well, it's a core principle and prediction of general relativity that clocks run slower in stronger gravity. So gravity alters space and time, and it's because in the general relativity theoretical framework, space and time are connected. So really, you can't alter one without the other because they're literally tied together in the equations. So you have an idea for gravity that alters mass, that alters space, curvature of space. It's also going to alter time too. And the way this plays out is that clocks run slower in stronger gravity. This was confirmed half a century ago on the Earth, which has quite modest gravity, so it's a very subtle effect, by using atomic clocks, the most accurate timekeeping pieces. by having two identical atomic clocks and flying one in a high altitude spy plane, essentially, and the other keep leaving in the lab on the Earth, and then bringing them back together to compare how they kept time, it was indeed shown that the clock on the Earth's surface kept very slightly slower time than the clock that was flown at high altitude by about 1 part in 10 to the 15, and 1 part in 1,000 trillion, so very, very small effect, because the Earth's gravity is modest. But in the theory, which is confirmed by those results, when the gravity becomes strong, this dilation of time becomes extreme. And in the most extreme form, at the event horizon of a black hole, the dilation of time is infinite, which means that time freezes at the event horizon of a black hole. Now, that's a prediction, of course, that we have not been able to test yet.
The next question is from Ranganathan, who asks, Ramani Ranganathan, who asks, the black holes come in different sizes and mass. Is there any conclusion we can draw from this, especially about what is going on inside black holes?
Well, it's an interesting fact of astrophysics that nature seems to know how to make black holes with an enormous range of masses. There's one set of black holes that result from the death of massive stars, and those are the ones that have been detected merging by the LIGO experiment, and they've been detected in binary systems by astronomers. So we know of dozens of examples of those black holes, and those range from about 3 or 4 times the mass of the Sun to 30 or 40 times the mass of the Sun. And then there's a whole set of black holes that form at the centers of galaxies by the collapse of matter, normal matter like stars and very dense situations in the center of a galaxy. And those black holes have a phenomenal range of mass. They range from, as far as we've seen, about 1,000 times the mass of the Sun up to 10 or 20 billion times the mass of the Sun. So their formation mechanism is quite different because they form in the center of galaxies. And so there are two fundamentally different types of black holes, the ones that are left over from dead stars and supernova explosions, and the ones that form dynamically in dense regions of the centers of galaxies. But taken together, they span a phenomenal range of mass of fundamentally the same object, a black hole.
The next question is from Paul Melnick, who asks, the Pentagon is ready to release a UAP report with much media fanfare. Do you see any explanations of these sightings?
Well, it's been a hot subject, as we all know. I wrote an article for The Conversation online journal a few months ago, actually, December, about UFOs and how I didn't think there was convincing evidence for aliens visiting from all those sightings. And that's had a lot of activity, 500,000 views and 600 comments so far. And it's just getting more and more as time goes by. The Pentagon is going to drop their report on Congress in a couple of weeks, near the end of June. And enough of it's been leaked that we know that they are going to not say anything definitive. They're going to deny that these sightings, these UAP sightings, unidentified aerial phenomena, which is a rebranding of UFO by the military because of the stigma attached to the UFO phenomenon. They're going to say that this does not represent a stealth U.S. military technology. They're not going to confirm or say that it represents evidence of aliens either. And that essentially, of course, will leave the door slightly open for people who want to think that it's alien visitations. It also definitely leaves the door open that these might be military technologies of some of the United States' rivals and enemies, like the Chinese or the Russians. It's going to be actually hard to pin this down because the evidence that's being leaked out there in these videos, it seems impressive at first glance, but for anyone who wonders and just thinks, oh, this has to be aliens, no way objects could move this fast, these are Navy pilots, they're trained observers. Well, they're trained observers, but they're not trained in everything, and it's very easy to be misled when you're in a plane above clouds and in strange situations. There's a guy called Mick West who's very cleverly and quickly shown that several of the Navy videos that have caused so much attention can very simply be explained by optical artifacts and just mistakes or illusions that pilots were misled. Rather mundane explanations for something that seems so dramatic. And I think that's the way it's going to be. I think when we get more evidence, we're going to find out that there are simple or mundane explanations for almost all these pieces of evidence, including the ones that are going to get released to Congress. Now, will that explain everything and mop everything up? Probably not, but that's how science works. You explain the most things you can with the simplest hypothesis, and the simplest hypothesis is not alien visitations, because that has so many other implications and consequences. And then if you find something that can only be explained by an alien visitation, then you go in that direction. And I emphasize that phrase, can only. The bar is set very high, and it's not going to be coming from some visual evidence or even videos. It's going to be coming from physical evidence. That's the only thing that truly will convince scientists.
The next question is from GN Vickus, or Vickus GN. As you know, China has created an artificial sun, which has a temperature of up to 116 million degrees and lasted about 30 seconds. What is the significance of this, and can we use similar technology to create a black hole on Earth?
Yes, the Chinese have made significant progress in sort of controlled fusion and very high energies and densities in the lab. It's similar research to what's being done in the United States and Europe and Russia. They've made some real strides in this area. So the goal, of course, in the conventional power scenario is to have a fusion reactor where there's no radioactive waste. It's a clean reactor that's using the power source that the sun uses, and all stars like the sun. As far as the relationship between these experiments and black holes, they're very, very far from creating black holes. The level of energy density and temperature that would be required to create something that has the attributes of a black hole are far beyond these experiments. Just to give you that example, in a supernova situation where the collapsing core of a massive star does create a black hole, the instantaneous temperatures in the supernova blast wave are tens of billions of Kelvin. And so again, that's hundreds of times larger than the temperatures that have been achieved in the Chinese experiment. So we're very far from the realm of creating black holes on Earth.
Another participant, Angela, would like to know why you think the UAP report is being disclosed at this time. What do you think realistically are the reasons that it's happening now as opposed to, earlier? Because these incidents have been happening for a long time.
Well, the military has been under, especially the Navy, where most of these sightings are emerging from, has been under a lot of pressure to be more transparent. As we know, the military, the government, hasn't been investigating UFO reports really since the beginning, since Roswell, since the 1940s. And there have been a series of reports and some information made public and some not. In the more recent time frame, the last 5 years, the Pentagon has been under a lot of pressure to release the data it has, especially on these videos and these Navy pilot sightings. And in fact, some of those videos were leaked about 4 years ago. And that sort of forced the Pentagon's hand. They actually had to be more transparent. And then in last year, some more data was leaked. And so the Pentagon, also under pressure from Congress, various people, Harry Reid originally, the Democrat majority leader, had strong interest in the UFO phenomenon and was pushing the military to report it. More recently, Marco Rubio and other politicians have been pressuring the Pentagon to be transparent. And so the political pressure has amped up enormously in the last year. And that's what's leading to what will happen later this month. They have essentially been told by Congress, you have to report on this. Some parts of their report will be redacted and will be classified. And of course, that will give cover to conspiracy theories. Since they don't release everything, conspiracy theory will hold that, of course, that's the alien evidence that they're just not telling us. But they are going to release a lot of information along with their best interpretations of what it is.
The next question is from Paulo, who asks, what can we discover about the universe from studying gravitational waves?
Looking at gravitational waves shows us the universe in a brand new way. It's very fundamental. Almost everything we know about the universe comes from light. The way light is emitted, absorbed, reflected, or scattered by objects in space. That's starlight, that's galaxies, that's essentially everything we know about the universe, except dark matter itself, which doesn't interact with light. So almost everything we've learned in 100 years or even 400 years since the telescope is about light and radiation. Gravitational waves don't care about radiation. That is essentially looking at mass directly, as if we had gravity eyes. And so gravitational waves are created anytime a mass distribution or configuration changes, or mass changes in the universe. So it's a dynamic situation, and that's what creates the oscillation of space-time called a gravitational wave. So it's a fundamentally new and different way of looking at the universe. And so what we're going to learn is fundamentally new and different. Now, it's only been around since 2016, the first gravitational wave detection. So it's a very young science, and our sensitivity is still modest, and our number of events is still only a few dozen. But in the future, this is going to be a very profound way of looking at how mass in the universe behaves, and eventually maybe how the early universe behaved. There's some hope that gravitational waves were produced and are detectable from close to the Big Bang itself.
The next question is from monasmehta, who asks, is it possible that we live in a simulation?
An interesting question, of course, and the simulation hypothesis, which was not originated by, but it was made popular by a philosopher called Nick Bostrom, who works at the Future Institute at the University of Oxford. He's argued that there's some finite and significant probability that we do to live in a simulation because of the likelihood that some advanced civilization, not that much more advanced than us, could create simulated entities like us, purely computationally. And the verisimilitude or reality of these simulations will be such that we couldn't tell the difference between being in a simulation and being in real life. That's the basic idea. And some various, people have talked about this, not just Bostrom, but Elon Musk has famously said he doubted that we lived in base reality. He thought it was much more likely that we were simulated. Okay, well, Elon Musk is a very clever man, and he was trained as a physicist, but I don't think he has any particular insight on the simulation idea. So it's an idea that's intriguing. It was originated by philosophers, and it's still philosophically a very fruitful and interesting hypothesis. It's not really testable in any way because almost by definition, this simulation that we live in would be so perfect we wouldn't be able to tell we're in a simulation. So at that point, it becomes a slightly sterile hypothesis because you can't test it.
The next question is from World of Science, who asks, there was a follow-up question that I wanted to ask. So what is some evidence that we could look for that would help us tell if we are in a simulation or not? Is there any way that we could run experiments to see if this is reality?
It's not clear because you'd have to know much more about the simulation that we're talking about. In the principle that the simulation is perfect or near perfect, this is not like the movie The Matrix where there are glitches in the Matrix, and so we can tell there's flawed programming. And so we can tell from these glitches or imperfections that there's something going on that's not right in our world. I think that's an unreasonable hypothesis. Any advanced civilization or technology able to create entities like us in all appearances and purposes would obviously be very sophisticated. So it's not clear that it's a testable hypothesis. And that's, I think, its fundamental problem, which is why it's remained an idea in philosophy and not an idea of science at the moment.
The next question is from World of Science, who asks, what impact does the quantum effect, or do quantum effects have on astronomy?
Oh, they have an enormous effect. So, modern astrophysics depends enormously on understanding of quantum principles. We couldn't understand how stars work without understanding quantum theory. The entire calculation of how fusion happens in a star like the sun depends on understanding the quantum behavior of nuclei and the way that they fuse, because classical theory doesn't tell you this. So our understanding of stars and how they function would not work. Our understanding of spectroscopy, which is how we measure what the universe is made of, through spreading the light out into a spectrum, and these are about quantum transitions of atoms and molecules, would not be possible. So our understanding of astronomy and astrophysics would be a pale shadow of what it is if there were none of these quantum effects. So quantum theory is sort of built into the heart of astrophysics and is essential for understanding the universe we live in.
Derek would like to know a little bit more about the asteroid belt, but I think they mean the Kuiper Belt. Can you please explain the asteroid belt that Pluto belongs to? Is there a larger star our solar system is revolving around?
So the asteroid belt, to make the distinction, the asteroid belt is, of course, a region between the orbits of Mars and Jupiter. It's quite extended in radius. And if you swept all that material up, it would be about 4% of Earth mass. So it's pretty likely that was a failed planet in the formation phase of the solar system. The Kuiper Belt is something different. It's another set of rocky objects that range from, small meters across to hundreds of kilometers across, asteroid size, that occupies a region between 40 and 80 times the Earth's sun distance, 40 to 80 AU. And so that places it somewhat beyond the orbits of Neptune and Uranus and Pluto. So it's a region of a large amount of rocky material. There's some objects in there that are likely to be Pluto-sized or bigger. There are already a couple known to be Pluto-sized, and they're likely to be more. It also could represent material that failed to form a planet early in the history of the solar system. And our understanding of the Kuiper Belt is fairly limited because it's far enough away. These rocks are just shining by reflected light, and the sun is that far away that they're very dim. So with Earth-based telescopes, it's hard to study the Kuiper Belt. New Horizons space mission went through the Kuiper Belt on its way past Pluto, and now is exploring the Kuiper Belt directly. And we've had a couple of missions reach out into the solar system beyond Pluto. So we've learned a few things about the Kuiper Belt, but it's a sort of unexplored part of the solar system for the most part.
All right, we have a bunch of questions from various folks about black holes, and I just want to mention that we answer a lot of questions about black holes. So if you have a question that we do not get to today about black holes, make sure you go check out our previous live sessions, because we have a huge collection of great questions and answers about black holes. That being said, since there are people who are interested, I'll try and throw a couple in here. David Wismer asks, if quantum information has to be conserved, how does information generated inside a black hole get out?
Well, that is, of course, an issue with black holes. It's called the information paradox. So there's a problem because information is generally preserved in quantum interactions, particle interactions. You can think of particle interactions as having some sort of information, the particle state before they interact and after they interact. Well, if that particle interaction occurs at the event horizon and then the particles go inside the event horizon, or some of them, then that information is lost. And that is a conundrum that's called the information paradox. Nobody knows what the resolution to the information paradox is. It's very active research. Some people speculate that entanglement, quantum entanglement, somehow preserves the information across the event horizon due to entanglement. There's no evidence for that. Some people excuse the information paradox by saying that the black hole creates a firewall around it, which is essentially an intense radiation field where the information is basically burned or lost due to this firewall. But again, there's no evidence for that. So it's pure speculation, and it's frontier theory of black holes. There's no simple answer to that question, because lab physics would have quantum information preserved, and a black hole event horizon seems not to preserve that information. The holographic principle is one other type of explanation, which says that as objects fall towards the event horizon, as seen from the outside, they take an infinite amount of time to reach it, and so perhaps the event horizon itself has the coded information of these asymptotically slowing down time clocks of particles imprinted on it like a hologram. Could you read the information of that hologram? It's not clear. So this is one of the ideas people are pursuing, but there's no resolution of this issue at the moment.
The next question is from one of our live participants. Let me see here. I lost my window. It is from Astronomat, who asks, is time continuous or discrete?
It's an interesting question. In classical physics theory, time is continuous. In relativity, in special relativity and general relativity, Einstein's theories of space and time, time is continuous. Now it's malleable, it's supple in the sense that we can have time dilation and space and time are connected in general relativity, but it is not quantized in any sense. And that does distinguish it from space, because it's possible that space is quantized. Certainly particles within space are quantized. Theories that go beyond general relativity accommodate the possibility that time is quantized. String theories, for example, do this. But there's no evidence that time is quantized. In other words, no lab experiment as we speak has ever shown that time is anything other than continuous in the lab.
So the next question is, if light bends near heavy objects, why is it not that the present of an object can be seen first and then its past, breaking time continuity?
Well, the prediction of general relativity is that the mass and energy curve space and time, where the mass energy is hyphenated, so it's both entities, and the space-time is hyphenated because they're connected in general relativity. So when we see light bending, gravitational lensing, for example, we're witnessing the effect of space-time curvature caused by the presence of mass and energy. Now that does actually alter the clock, as mentioned earlier. Clocks run slower in stronger gravity, so as a light beam is deflected near a massive object, its clock essentially slows down while it's in the stronger gravity. But that doesn't create a causal problem. The slowing down of time does not ever imply its reversal. And so I don't think you have any causal problem or paradoxes arising from the bending of light by massive objects.
The next question is from Jose Luis Escalante. And this is more of a personnel question. In your experience, does astronomy attract more atheists or more religious people? What is your wild guess what the proportion is?
Well, I've seen surveys of scientists as a whole, not just astronomers, and the Pew Research Organization and a few others have surveyed scientists, professional scientists, and the fraction of atheists is maybe not as high as some people might imagine. It's about the same as the number of conventional sort of church-going religious people. It's about a third. So that's the number I've seen across sciences. I don't know if the fraction of atheists amongst astronomers is higher than it is of biologists or physicists. I would have no way of guessing, in fact. So atheism in the general population in the United States is quite small. So scientists are definitely more prone to be atheists than the general population, but they also include a large fraction of people with conventional religious views.
The next question is from Subham, who asks, is solar radiation pressure affecting the trajectory of space debris?
Interesting question. Basically, the answer is no, because solar radiation is a real effect. Obviously, the photons from the sun carry momentum, and we have the technology called a solar sail, which is involved with making gossamer thin sheets of material like mylar and harnessing the momentum of solar wind or solar photons to project something, propel something through space. So since you can do that, it obviously must have an effect on normal matter. But space debris tends to be small chunks of dense metal, and so their reflective surface area is actually quite small. And so the amount of radiation pressure and momentum carried compared to the momentum they have as orbiting objects around the Earth is tiny. And so in practical terms, no, solar radiation pressure does not routinely alter the trajectory of space debris. What tends to be more of a significant effect is the fact that even in upper elevations of low Earth orbit, there's a tiny amount of atmospheric density, and that creates drag, and that's what slowly alters the trajectory and causes space debris to spiral in and burn up. That's the main effect we see.
The next question is from P, who asks, DARPA has funded studies into the Cassimir effect to possibly be used for future aerospace vehicles. Can you explain this effect and how it could be used to leave Earth's gravity?
The Cassimir effect is an effect of the vacuum that's manifested in the laboratory on the Earth. I mean, I think it was first observed almost half a century ago, where you can, in a vacuum between charged plates, you can create a certain amount of energy density. And in principle, this energy density could be extracted or harnessed to create a propulsion system. It's an entirely theoretical concept, though. No one that I know of has proposed a viable technology based on the Cassimir effect. It's one of the ideas under investigation for advanced propulsion in space. But I actually think more conventional ideas like ramjets and fission plate reactor devices are more likely to produce new propulsion ideas than the Cassimir effect.
All right, well, it is 9:59, so we are at the end of our time for today. We have one more question that we will end with, and then we can say goodbye till our next live session. So Subham G asks, will the James Webb Telescope also have capabilities to detect gravitational waves?
The James Webb Space Telescope, due to be launched fairly soon, is a nominal replacement for the Hubble Space Telescope, but its capabilities are pushed more into the near-infrared than the visible. So it's a conventional telescope detecting optical and near-infrared light. It does not have a capability of detecting gravitational waves or gravitational radiation, so no, it will not be doing gravitational wave work. NASA does, however, and ESA, the European Space Agency, have a joint project to launch a gravitational wave interferometer into orbit called LISA. And this is based on the technology of LIGO taken into Earth orbit, where a free-flying interferometer will be able to detect gravitational waves. The Pathfinder mission, a miniaturized version of some of the technologies, was quite successful a couple of years ago. The full-on mission that could actually detect gravitational waves is a lot more ambitious and more expensive, and the time frame for that is about 10 years, but it's probably going to happen. Okay, thanks for your questions again, all on good topics and good variety, and we'll be with you again and announce the next session soon.